Okay, hello and welcome back. In the last lecture, we defined what's a directed graph and what was it. It is basically a pair of sets, the set B of the vertices, and then set A of arcs, which are ordered pairs of uh, elements of V. So the difference from that of the ordinary graph is that instead of two element subset, we have ordered pairs of vertices. Now this enables us to visualize the graph as having some kind of direction for the edges. That like if 1, 3 is an ordered pair, I can represent by drawing a curve connecting 1 to 3, but with an arrow which says that it's actually going from 1 and going to 3. So therefore, the direction is represented by the arrow, and that tells you also what is the arc, right? What is the ordered tuple, right? When I have 1, 2 as the uh, elements of the two element set, then the direction comes by seeing that there is an arc from 2 to 1. So therefore, 2, 1 must be the corresponding arc. Now, here is an example of a digraph where V is the set 1, 2, 3, 4, 5. Then we have A set 1, 3, 3, 4, 2, 1, 2, 4, 4, 5, and 5, 4. Now there is 4, 5 as well as 5, 4, which enables us to go from 4 to 5 as well as from 5 to 4 by taking an arc. On the other hand, if you look at 2 and 4, I can go from 2 to 4, but there is no way to go from 4 to 2 in this case. So it's important to have this direction, and that allows us to represent more information about the network. For example, when you have a traffic network where some of the roads are one ways, then we know that we cannot have bidirectional commutation, and hence this will allow us to represent traffic networks better. Now, if you look at the set of all vertices, the multi-set of all vertices is that xy is an arc. It's called the out degree of x. These are the number of edges which goes out of x, right? So start from x and go to some other vertex. Then it is usually denoted by d plus of x. That says that the out degree of the vertex x. And similarly, the multi-set set of all y is such that yx is an arc, is the in degree, which means that all the r's which are coming into y, that is denoted by d minus of x. So we have the out degree as well as the in degree. Now, if you think about this, one can see that if I have an arc from any vertex, let's say x to y, then of course, it contributes 1 to the in degree of x and 1 to the out degree of y, right? So therefore, the following theorem is immediate, that if you look at d equal to b comma a as a digraph, then sum over all the vertices d plus of v, right, the out degrees, is equal to sum over all the vertices in degree of v, right? So the out degree sum must be equal to the in degree sum, which is equal to the cardinality of the arc set, right? How many arcs are there? So this is immediately clear, and the proof also we have just mentioned. Now, in digraphs, we usually also allow loops. That is, you can have V to V as an edge, right? Where I go from V and then comes back to V. And these are called loops. And often we consider this kind of loops, digraphs. But of course, we also discuss loopless digraphs most of the time, and then only when we require, we will mention it and then use it. Now, the degree of a vertex is the sum of the in degree and out degree. Right? That is the number of edges which is actually going. So you can also see this as the as the degree of the underlying graph where we discard the directions, right? So if you see the edges, right, as the arcs as edges rather than directed edges, then you'll get a multi-graph, right? You can get a multi-graph where you allow multiple edges between a pair of edges, and then you can see that it is basically the degree of the multi-graph. So therefore, one can talk about the underlying graph of a diagram. Then the loops usually count for 2 for the degree of a vertex, because the in degree is there and out degree is there. And for the undirected case also, most of the time we will do that. Then very similar to what we did in the undirected graphs, we can define directed walk, path and cycle, where a directed walk is basically a sequence of vertices v1, v2, etc. vk, where vi plus 1 for every I less than k is an arc, right? So we need to have arcs in that particular direction. So, right? So this is a directed walk. Now, if the vertices are not repeated, right? One vertex only appears once, then a directed walk, as in the case of the undirected graph also, it's called a directed path. So here I have a graph, a directed graph. U and V are there, and then you have arcs going from U to V, right? So UV is an example of a directed path. On the other hand, 1, 2, 3, right? Here I have written in yellow or greenish yellow, is basically not a walk or a path, because 1 to 2 is an arc, but 2 to 3 is not an arc. So 1, 2, 3 cannot be a path or a walk. On the other hand, 1, 2 is a walk and a path. 3, 2 is a walk and a path. Right? So therefore, now a directed cycle, just like in the case of undirected case again, right? If P is a UV directed path, then you add the arc V to U also, then that is a directed cycle. Right? So U to V and then coming back to U from V directly. So examples are in this graph above, right? So you can see that 1 to 3, then 3 to 2 and 2 to 1 is a directed cycle. Right, so this is a directed cycle. And then you have 1 to 5. One to 5, 5 to 4, 4 to 3, 3 to 2, 2 to 1. Right? This is another directed cycle. But on the other hand, 1 to 6, or like 5 to 6, 6 to 1, and 1 to 5, even though it's a cycle, it's not a directed cycle, right? It's a cycle in the undirected graph, but on a directed graph, it is not a cycle. It's not a directed cycle. Now, we define a special type of digraph. It's called functional digraphs. So functional digraphs are basically digraphs which can represent endo functions from a set to itself. Now let us take a digraph with a vertex set V, and then we say it's a functional digraph if the out degree of every vertex is actually equal to 1, right? So every vertex has exactly one edge going out of it. It could have many coming inside, but going outside is exactly one. And this you can see immediately why it should be the case, because if you are defining a function, it can only have a unique image. It cannot have multiple images for an element, right? So here is an example of a functional digraph where if you look at any vertex, you will see it has exactly one outgoing edge, right? So let us see that. Vertex 2 or 1, right? It has exactly 1. Then vector 3 has 2 incoming but 1 outgoing. 5 has 1 outgoing. 4 has 1 outgoing, right? 6, then 8, 7, and then 11, 10, 9. All these things has exactly 1 outgoing arc. And you can verify for other vertices. So what we have is a functional diagram. Now, why is it called functional diagram? Because it actually represents a end of function from V to V, right? So you can see the function by just looking at what each element is mapped to as the out neighbor of the vertex. So out neighbor of a vertex is the vertex which is obtained, which is a neighbor through the outgoing arc, right? So in this particular example, we have f of 1 because 1 is going to 3, f of 1 is equal to 3. Similarly, 2 is also going to 3, so f of 2 is equal to 3, right? F of 3 is 4, f of 5 is 4, right? And similarly, you have all these values, right? F of 14 is equal to 14 because there is a loop there, right? And yes, so this is how it is. Now, what I want you to do is to draw a few functional diagrams by yourself and then try to see whether you can observe any nice properties about this. So if you think about this and then come up with some observation, that would be very nice. Now, we say a vertex in a functional diagram to be cyclic if it belongs to some cycle of the diagram. Okay, so any vertex that is part of a cycle is called a cyclic vertex. So in the previous example, right, we saw that like the vertices 14 is cyclic because 14 is in a loop. Then 12 and 13 are cyclic because 12 to 13 and 13 to 12 are also arcs, which forms a directed cycle, 2 cycle. And then we have this other part, right, where we have 4 going to 6, 6 going to 8, 8 going to 7, and 7 going to 4 again, right? That's another cycle. So 4, 6, 7, 8 are again part of a cycle, so therefore they are cyclic vertices. So we have this 1, 2, 3, 4 plus 3, 7 cyclic vertices, right? So these are the cyclic vertices. Other vertices are not cyclic because they are not part of a cycle. Now, suppose you have a functional digraph, and if suppose if this graph has exactly one cyclic vertex, right? In the entire graph, there is only one cyclic vertex. Then we call this digraph as a rooted tree. The rooted tree is basically a functional digraph where we have exactly one cyclic vertex, right? And the root of the vertex is the vertex having a cycle. So in this example, you have 7 as a root of the functional digraph because 7 is a single cyclic vertex which is in a loop, and every other vertex you can see has exactly one outgoing edge, so therefore it's actually a functional digraph. So we have a rooted tree now, right? The rooted tree is basically a functional digraph with exactly one cyclic vertex. Now I give you some homework questions. First, define 5, let's say, different functions from a vertex set 1 to 12, let's say, to itself, and draw corresponding functional diagram. Okay, and once you draw this, look at the properties of it. So draw the functional diagrams each on two functional diagrams each on 8, 9, and 10 vertices. Then write the corresponding functions. Now, if you have observed some properties after drawing several of these, you must have seen some few properties. Then what are these properties that you have seen? So make a note of that and try to write it. Now try to prove each of your observations and see whether this observation is actually a property for the entire functional diagraph or not. Now if you have a graph let's say G, then every closed walk of odd length contains an odd cycle. Okay, this is not for directed graph. I'm asking you to prove for normal graphs. Okay, so given a graph G, then every closed walk of odd length contains an odd cycle. So this homework you must do, because we are going to use it to prove something else. Now, some properties of functional diagrams. Okay? So we are looking at functional diagraph of special type of functions now, which are the permutation. So permutation is a bijection from a set to itself. Right? So we have the following permutation. Let's say P, which takes 1 to 7, 2 to 8, 3 to 4, 4 to 3, 5 to 10, etc. Right? 9, 10 to 1. Now, what is the functional diagram of this permutation? So, if you look at the functional diagram of this permutation, you will see something interesting, right? If you look at this functional diagram, you will see that, well, you have 1, 7, 1 is going to 7, because 1, 7 is the map. Then 7, what happens to 7? 7 goes to 5, right? So, to draw the diagram, you basically do this, right? Define the function and then you look at what happens. So, 7 going to 5, then 5 goes to 10, then 10 goes to 1, right? So now that is one cycle. Then we have to start with the next available one, right? So I start from 3, 3 to 4, then 4 to 3 again comes back, another cycle. Then you start from 2, right? 2 to 8, 8 to 6, and 6 to 2 again, right? And similarly, 9 is mapped to itself, so therefore it's a cycle. So if you look at this, you will see that all the like it's basically a collection of cycles, right? Every vertex is part of a cycle. Now, this one can see why it should be true in the case of permutation, right? Now, this also gives us an inkling that why basically permutation can be represented as cycles, right? So we have cycle represented permutations, which comes from the observation that the digraphs of the permutations are basically a collection of cycles. So you can try with several examples, right? Try to define certain permutations, draw the functional diagrams, and see whether you have the same problem. Now, the functional diagram of permutations is a collection of cycles, right? This is an observation that you can immediately make. And then if you inverse each arc of the diagram, right, then we get the functional diagram of the inverse of the associated permutation. So again, like if you map from 1 to 10, 10 to 5, then 5 to 7, and 7 to 1, etc., then you will get what you get is basically the inverse of the associated permutation and the corresponding functional diagram. Now here is a theorem we want to prove, right? So if f is a bijection from V to V, then the functional diagram of V is a disjoint union of directed cycles, right? So we can now prove it formally. So I want you to think about the proof before you go ahead with this proof, but it would be nice to do that. Now, how do you prove this? So we know that f is a bijection, right? So it's a bijection, which means that every element of V has a unique image and a unique pre-image, right? So by the definition of bijection, there is a one-to-one correspondence, right? So every element has an image and it has also a pre-image, unique pre-image. Now, which means that every vertex of the functional diagram. So if you look at the functional diagram, you know that it has exactly one outgoing edge because it is a functional diagram anyway. But it also has exactly one incoming edge, right? Now, if the number of so the outgoing edge is 1 and incoming edge is 1. So which means that if you look at the underlying graph, right, without the directions, then what is it? It is basically a every vertex has degree exactly 2, because one is actually the outgoing vertex, outgoing arc, and one is the incoming arc, right? These two contribute degree 2. Therefore, we see that the underlying graph, every vertex has degree 2. Now, it's a simple exercise to show that if a graph has the property that every vertex has degree exactly 2, then it is basically a collection of cycles. Right? So this will allow us to see why this should be the case. The permutation must have a collection of cycles. So out degree is equal to 1 and degree is equal to 1. Since every vertex has degree 2, it must decompose into disjoint union of cycles. So I want you to prove this formally, write a proof. But it is kind of obvious, right? But then try to write it formally. And this is true only because we assume that V is finite, right? If for infinite vertices, you can have just a path where I mean, yeah, we can have a tree, for example, right? Where every vertex has degree exactly 2, and then it need not hold. Now, since every vertex has d plus of v is equal to 1 and d minus of v is equal to 1, right? The cycles must be directed cycles. Now, can you see why? Right? So, every vertex has the out degree and in degree equal to 1. Then, the cycles in the graph must all be directed cycles. Because if it is not directed cycles, you will see that some vertices cannot have this property. Now, we have another proof now using walks. Okay, so start from any vertex u and take a walk. Right, since every vertex has an out neighbor, the walk contains continues for any length. Right, because the I start from a vertex, then I go to the next neighbor taking the out degree. Now I have taken an incoming edge to go here, so therefore now I can also go out of this. So I go out of it to another vertex and then I continue. Right. So I keep on continuing this, and I can do it as much as I want because every time I reach a vertex, I can go out of. But now, since the graph is finite, this walk cannot be infinite, right? So I mean, walk can be infinite, but the walk must repeat vertices because we have only finitely many vertices. So I start from a vertex, then eventually it must come back to some vertex. Now, the first vertex that repeats must be the starting vertex u itself. Why is that? Can you think of this? So try to see if I have a functional diagram, and then we start from a vertex, then you go because every time you can go out of it, and then if eventually a vertex is repeating in the case of permutations, eventually if a vertex is repeating, then it should be the starting vertex itself. It need not be the case for functional diagrams, arbitrary functional diagrams, but for the permutation case, it must be the vertex u itself. Now, why is that? Because if that is not the case, the repeated vertex, right? What happens is I start from u, I go to let's say v, and then go further, and then suppose it comes back to v, not to u. Then, if you look at the vertex v, right? So we already had an incoming edge from u, right? And then outgoing edge that we took as part of the walk, and then coming back without visiting u, we means that I am basically having another incoming edge to the vertex v. So I have two incoming vertices. So in degree is at least 2. But we said that the in degree is exactly 1 because it has only pre-image, unique pre-image. So therefore, we see that like if I start from a vertex, after some time it must finally come back to the starting vertex. So now that forms a cycle by the definition of cycle, right? I have a sequence of vertices without repeating anything except the first one is repeated, right? Then you get a cycle, directed cycle. Now I can throw away these vertices, right? Because all the ingoing, incoming and outgoing edges are counted now for these vertices. So I throw away. And then remaining I can start again, right? So therefore I get a decomposition into cycles. So here is another different. Now as a homework, I define the following. I let C of nk as the number of permutations of an n-element set whose functional digraph is a disjoint union of k cycles. Okay. So the number of permutations whose functional digraph is a disjoint union of k cycles. Exactly k cycles. So that C and K satisfies the following recursion formula. C and K is equal to C of n minus 1 comma k minus 1 plus n minus 1 times C of n minus 1 comma k for 0 strictly less than k less than n with the initial conditions that C of n0 is equal to 1 if n is equal to 0, it is equal to 0 if n is not equal to 0, and C of nn is equal to 1. So this conditions lets you calculate C and K uniquely and find out this, right? So you can think about this. The next notion I want to look at in this case is that of connected. So given a graph G, we say the graph G is connected if and only if for every pair of vertices there is a UV walk in the graph G. Okay. If there is a UV walk for every pair of vertices, then the graph is said to be connected. Now, if you are looking at digraphs, we say the digraph is connected if for every pair of vertices is strongly connected if for every pair of vertices there is a UV walk, directed walk, right, in the digraph. Okay. So, in the case of graph, we say the graph is connected if any two vertices has a walk between them or a path between them. Similarly, we say a digraph is strongly connected if for every pair of vertices I can reach any vertex from any other vertex. So here are some examples. The first one is basically an undirected graph where which is not connected because it has several several parts where I can go from 1 to 2 and 2 to 1, but I cannot go from 1 or 2 to, let's say, 3, right? So there is no walk or path from 2 to 3. So therefore, this graph is not connected. So you will see that there are several such parts, and each part is basically connected, right? Then you have the directed graph, which is not strongly connected, even though the underlying graph is connected. Right? You have this second case where you cannot go from one of the vertices to the other. For any pair of vertices, right? For example, I can go from this vertex to here, but I don't have any way to come back from that vertex to this vertex. So therefore, it is not strongly connected. Then again, another example of not strongly connected graph, because in this I can go, for example, from let's say this vertex. Let me give some names. Okay, so this is 1, 4, 5, 6, and 7. Now I can go from 1 to 2, 2 to 3, 3 to 4, 4 to 1, etc. Right? But if I want to go, for example, from 6 to 2, right? I cannot go from 6 to 2. Right? I can go from let's say 2 to 5, 5 to 6, right? I can go from 5 to 7 and 6. Similarly, I can go from 6 to 5 and 6 to 7, but I cannot go from 6 to 3, right? Or 6 to 2. So therefore, this is also not strongly connected. Then here is a strongly connected example where I can go from any vertex to any vertex, because I can go from, for example, vertex 1 to vertex 2, right, by taking any path, 2 to 1, and similarly from 2 I can go to here and come back. And then you will see that all these can be reached from any other vertex to any other vertex, and therefore we have a strongly connected now. Given a directed graph D, we sometimes look at the R's as the undirected edges, as I mentioned before, and consider the underlying graph, right? So an example, the directed graph D is represented here, and the underlying graph of D, where we just discard the directions, right? So all the ordered tuples now becomes just two element sets. Now this could be useful in several occasions. So we will we'll see that. Now a digraph is weakly connected if its underlying graph is connected. So if you just look at the underlying graph, see that it is actually connected, right? Then we say the digraph is weakly connected. I mean, it's not strongly connected because I cannot go from anywhere to anywhere, but it is weakly connected in the sense that, you know, from you know, the underlying map allows us to go. For example, if I have a transport network where some paths are one ways, then of course you cannot go from a vertex to, you know, a point to another point, maybe taking an edge. But on the other hand, it says that, you know, in case of some special situations, there is a possibility of reversing the decision to make it one way, right? And then you can allow other direction passing. You know, it's not the excellent example or anything, but to say that why the weakly connectedness can be useful in some times. So a strongly connected graph is of course weakly connected, right? Because if you can go in the directed graph, you can always go in the undirected graph. Now, as a homework question, you can think about the following: that G is any graph or a digraph, and if you have a pair of vectors U and V, then there is a UV walk in G if and only if there is a UV path in G, right? So for graphs and digraphs, one can show this, right? So UV walk if and only if there is a UV path. So this you can try to prove or disprove if it is not true for either graph or digraph. And this will be a nice homework.